Hello and welcome to my presentation today. My name is Andrew Altoff and I will be presenting the results of my research that I conducted alongside my advisor, Dr. Michael Lewison. The research I will be presenting to you today is titled Depth-Based Barotrauma Severity, Reflex Impairment, and Stress Response in 2 species of ice-angled fish. So I'm sure the first question you have is, what is barotrauma? So barotrauma is physical damage that occurs to fish when fish are brought to the surface too quickly, often during angling. And this damage is a result of swim bladder overexpansion. So the swim bladder is an organ that most fish possess that helps them maintain buoyancy at different water depths. And if I take you down to this diagram of the swim bladder over here, you can see there are 2 points on the swim bladder, and these 2 points are called the ovale and the rete mirabile. And these are points where gas will actually enter the swim bladder and help it inflate. And more gas will enter the swim bladder, and the swim bladder will expand more when the fish is holding at deeper depths, because there is increased external pressure of the water on the fish at those depths. And this swim bladder will expand as the fish rises in the water column because of a decrease in the external pressure of the water. And so barotrauma happens when the fish rises in the water column too quickly due to a sudden decrease in the external pressure of the water. And barotrauma is defined by a variety of symptoms. So if I orient you to this picture of this fish up here, this fish is very severely barotrauma. You can obviously see this is actually the stomach of the fish that is everted into the buccal cavity, into the mouth of the fish. Also, if you look at the eye is bulging a lot more than it should be. That is another typical sign of severe barotrauma. Also, this fish appears to be bloated in the organ region. That is another symptom of barotrauma. And you can't see it in this fish, but oftentimes severely barotrauma fish may have a prolapse of the cloaca, which is the area of their body where the anus and the urinal tract are. And there also may be some hemorrhaging in the fins and gills as well. So some of the background research and what we currently know about barotrauma is that the depth of capture, so the depth at which the fish are originally holding at when they are caught and brought to the surface, has a significant impact on the barotrauma severity in fish caught in warmer open waters. Also, the barotrauma severity has impacts in physiological stress response and likelihood of mortality post-release. However, these have not been tested in ice fisheries, even though the depth of capture may have a larger impact on barotrauma severity in colder water fisheries due to the fact that colder water is more dense, and the more dense water is going to put more external pressure on fish, so there is also going to be a larger decrease in the external pressure as fish are brought to the surface. So as far as venting goes, venting is a common treatment for fish that are experiencing symptoms of barotrauma, and it is done by inserting a hollow point needle into the swim bladder of the fish. However, the effectiveness of venting in treating barotrauma is debated. Some scientific studies have found it helpful for fish and that it was effective at treating barotrauma, while others have actually found it to be harmful in use when treating barotrauma. Also, if you are inexperienced at venting fish, there is the risk that you will injure the other organs of the fish while inserting the needle. So when we're looking at physiological impacts of barotrauma severity, a couple of impacts that we may be interested in include reflex impairment and physiological stress response. So when we're looking at reflex impairment, a lot of times we're looking at what are called reflex action mortality predictors, also known as RAMP. And the reflex action mortality predictors are a way to quantify the sublethal stressor effects and predict delayed mortality of post-release fish due to the reflex actions and impairment. Also, with stress response, a lot of times you're looking at blood glucose. And the reason why blood glucose is a good marker of stress response is during times of stress, glycogen stores of the fish are broken down, and this increases the blood glucose. And the increased blood glucose serves as an energy source for the fish to help the fish combat the stressor. And previous studies of physiological stress response in ice-angled fish have shown that the physiological stress response of blood glucose is delayed and prolonged in fish caught in colder waters compared to fish caught in warmer waters. So the three goals, what we were trying to look for and determine in this study. So our first goal was to determine how the holding depth of the fish under the ice affects the severity of barotrauma exhibited upon capture. Our second goal was to determine how this barotrauma severity, as well as the venting and holding time, impact the reflex action mortality predictor scores in ice-angled fish. And then our final goal was to determine how barotrauma severity, venting, and holding time impact the blood glucose stress response of fish. So this is our study site, this lake right here in this picture. This is Shadow Lake in Waupaca, Wisconsin. It is a very small lake. It's only 0.18 square kilometers. And it has a maximum depth of about 12.5 meters and a mean depth of a little over 5 meters. Common species in Shadow Lake include bluegill, largemouth bass, yellow perch, northern pike, and black crappie. So the angling methods that we used to capture our fish in this study: we began by drilling several holes in the ice at various depths using an ice auger. And then our anglers who assisted us in this study would go around and check each hole for fish using a Vexilar sonar unit, which is this object right here. And the way that they would look for fish, when a fish is in that area, the fish will show up on this little round dial as either a green, yellow, or red, little red line. And then once they found a fish, they would note the depth that the fish was holding. And then they would use standard ice angling gear, which is represented here. It consists of a short rod, less than 1 meter in length, so light line, and then we would use live or artificial bait. Once a fish was captured, the angler would bring the hooked fish to the surface as quickly as possible and would note the holding depth of the fish. And they were brought to the surface as quickly as possible in order to minimize the effects of fight time on barotrauma and stress. Now, for barotrauma assessment, all caught fish were immediately transported to one of 16 holding tanks, which you see here. Each one of these holding tanks was filled with water from the lake, from another hole that was drilled in the ice. And barotrauma was assessed by checking for 6 signs, which include the gastric herniation out the mouth, the prolapsed cloaca, hemorrhaging in the gills or fins, bloating of the stomach region, the eye bulge, and also a difficulty in swimming down in the tank. And fish were assigned severity based on the symptoms that they exhibited. They didn't have any barotrauma if they didn't exhibit any of the symptoms. They were assigned light barotrauma if they had difficulty in swimming down in the tank but exhibited no other symptoms. Moderate barotrauma if they exhibited difficulty in down swimming, as well as some bloating. And severe barotrauma if they exhibited difficulty in downswim, bloating, and any of the other symptoms. After barotrauma was assessed, fish at random were selected to be vented. And the vented fish were vented using a 22 gauge needle, and this was inserted laterally just beneath the vertebrae of the fish. And venting was deemed successful if we heard an audible sound of the gas escaping from the swim bladder. Once a certain population of the fish was vented, all fish were put back into the holding tank. Once fish were placed back into their holding tanks, they were either designated as controls or they were held for 1 or 2.5 hours. Control fish were processed immediately for ramping glucose and were not vented. And this led to the development of 5 treatment blocks. We had our non-vented controls, non-vented fish held for 1 hour, non-vented fish held for 2.5 hours, vented fish held for 1 hour, and vented fish held for 2.5 hours. Once the holding time of the fish was up, the fish were then taken for ramp testing, and ramp testing in the study consisted of testing for 4 reflexes. The first reflex was burst swim, where we would grab the tail of the fish to see if the fish swam away. If the fish did not swim away, that reflex was impaired. The next reflex was the body flex, where we would hold the fish limp in our hands to see if the fish kicked its tail. If the fish did not kick its tail, that reflex was impaired. The third reflex we tested was vestibular ocular response, where we would rotate the fish and look at the eye of the fish As the fish is being rotated, the eye should rotate as well so that the eye is always looking up. If the eye does not rotate as the fish is rotated, that reflex is impaired. And the last reflex we tested was the righting reflex, where we would simply turn the fish upside down in the tank and wait for the fish to turn itself right side up. If the fish could not do that, that reflex was impaired. And then fish were scored from 0 to 4 based on the number of impaired reflexes they possessed. After ramp testing was completed, the length of the fish was measured, and then we obtained the blood glucose reading. First, we obtained a blood sample from all of the fish by inserting a needle into their caudal veins from the ventral side, right between the anal and caudal fins. The obtained blood samples were placed onto glucose test strips, which were placed into the appropriate glucose test meter in order to obtain the blood glucose reading. After this, previously non-vented fish that were still exhibiting signs of barotrauma were vented, and all fish were released. So just some general fish capture results. We successfully captured 118 fish in this study and processed them. 76 of these fish were bluegill and 42 were black crappie. We did not obtain successful blood glucose readings from all of the fish that we captured in this study, but we were able to obtain them from 46 bluegill and 35 crappie, or 81 total fish. Now this table is looking at the top models and the factors impacting barotrauma severity. The top models were determined by eAEC information criterion. And if you look at these first three models, the models 1, 2, and 3, you can see their eAEC information criterion values are all within 2 of the top model, which is model 1. And then here we have our worst model, which is the null model in this case, which has an eAEC information criterion of over 81. And then we look at the different factors that were tested against barotrauma severity. In the top model, the top 3 factors were depth, species, and length. And over here we have the relative importance values of these 3 factors. Depth had a relative importance of 1, species had a relative importance of 0.86, and length had a relative importance of 0.85. So this means that the holding depth of the fish was the most important factor in impacting barotrauma severity. Okay, so here we have a set of 3 binary logistics plots that are showing the impact of increased holding depth on increased barotrauma severity. And the big takeaway here is that deeper holding depths led to more severe barotrauma upon capture. So if we look at the first binary logistics plot, this is showing the probability of fish exhibiting light barotrauma. So all these fish down here are exhibiting no barotrauma, and then all these fish up here are exhibiting either light barotrauma or even more severe barotrauma. And if you look, this one only has 1 line compared to the other 2 because these lines are comparing the 2 species, bluegill and crappie. We were only able to obtain 1 crappie that had no barotrauma in this study, so we could not fit a binary line for crappie in the light barotrauma. And then we go on to moderate barotrauma. Here we have bluegill, and then we have crappie. And what we're looking at here is we're really interested in about the 50% mark, which is where we would start. Beyond that, we would start to expect more fish to have moderate barotrauma as opposed to light or no barotrauma. And you can see that the bluegill, about the 50% mark, is maybe a little bit less than the crappie. So we would expect bluegill to start exhibiting moderate barotrauma at a slightly shallower depth than we would crappie. And then for our final plot over here, we have the probability of fish exhibiting heavy or severe barotrauma. And you can see there's an even wider gap in bluegill and crappie here, where the 50% mark for bluegill is at a shallower depth than it would be for crappie. So we would expect bluegill to show signs of severe barotrauma at a shallower depth than crappie. Okay, so this table here is looking at the factors and models predicting the importance in determining reflex impairment. So we look at our top models here. We have 5 models that are within 2 points in the eAEC information criteria. And then we again have our null model, which is our worst model, which has an eAEC information criterion value of 16. In our top model, the factors that were included were vented, barotrauma severity, the species, the length, okay, never mind, the length was not included, and the two-way interaction of species and venting. And we look at the importance values of the factors. Venting had a relative importance of 1, barotrauma severity had a relative importance of 0.99, and species had a relative importance of 0.8. The most important two-way interaction was the two-way interaction between species and vented at 0.52. So this means that venting was the most important predictor of reflex impairment. So we look at this graph. This graph is showing that venting helped bluegills much more than it helped crappie, and it actually may harm crappie. So if we're looking at this, these triangles here are the mean values obtained in ramp score. And we can see these white bars represent vented, or non-vented fish, and these gray bars represent vented fish. And so here we have bluegill, here we have crappie. You can see that there is a big drop in the mean and median ramp scores for bluegill that were vented as compared to bluegill that were not vented, whereas the mean ramp score actually increased for vented crappie compared to non-vented crappie, and the median score was about the same. And again, overall, this concludes that venting helped bluegills but may actually harm crappies. And then our final table here is looking at the most important models in determining the factors affecting blood glucose. So we have 4 models that were within 2 of the top model, and we have our null model, which again has an ICAIC information criterion value of 16. Our factors that were included in our best model were species, holding time, barotrauma severity, and fish length. And if we look at the relative importance values, species was the most important at a relative importance of 1, holding time was next at 0.89, and barotrauma severity was the third most important factor at 0.72. And this goes to show that species and holding time are important predictors of blood glucose. Okay, so this figure here is looking at the results of one-way ANOVAs that we ran, comparing all of the different treatment blocks back to the controls. And the first big takeaway here is that blood glucose is higher in crappies and increases as holding times get longer. So if we look at the blood glucose levels, here you can see that the blood glucose levels of crappie are much higher than the blood glucose levels here of bluegill across the board. And then we can see that as time gets longer, so here we have non-vented 1 hour, non-vented 2.5, vented 1, vented 2.5. You can see that the blood glucose levels rise, and there is significance in crappie in the vented 2.5 hours, and there is near significance in the non-vented 2.5 hours in comparison to the control. And then in bluegill, there was significance in all of the treatments with the exception of the non-vented 1 hour bluegill. The other big takeaway is that bluegill experienced a more rapid increase in blood glucose. As you can see that the bluegill had significant differences in their blood glucose levels at 1 hour, whereas the crappie you didn't see it until 2.5 hours. However, this may also be due to the small distribution of the control. As you can see, the control, there is much less distribution in the glucose levels of the control bluegill than there is in the control crappie. And then if we're going back to ramp scores, you can see again more clearly, much as like in the last graph, that the ramp scores were significantly reduced in vented bluegill, whereas they didn't really change much in the crappie. So the overall conclusions that we drew from these results is that when ice fishing, fish caught at deeper depths will exhibit more severe barotrauma, much like they will in open water. Fish exhibiting more severe barotrauma will have more reflex impairment and thus a higher risk of post-release mortality. Bluegill respond well to venting, while crappie are unaffected or harmed by it. Also, bluegills are more susceptible to physiological harm by barotrauma and are more susceptible overall to barotrauma than crappies. Both species exhibit similar stress response, although black crappies have higher overall levels of blood glucose. So what are the likely explanations for the observed results? So first, increased barotrauma severity associated with deeper holding depth can be explained by the pressure changes that occur when the fish is brought to the surface. So as a fish is holding in deeper water, it's going to be under more pressure than a fish that is holding in less deep water. And so there's going to be a larger pressure change as that fish is brought to the surface. Therefore, there's going to be more expansion of the swim bladder and thus more barotrauma. The increased reflex impairment and likelihood of mortality that is associated with more severe barotrauma is consistent with increased physical damage. If you have more severe barotrauma, your swim bladder is going to be expanded more. It's going to press more into the other bodily cavities of the fish and is going to cause more physical damage to the fish. As there's more physical damage, the fish is much more likely to suffer from post-release mortality. So what could explain the difference between the black crappie and the bluegill in the susceptibility to barotrauma and the physiological responses to barotrauma and venting? So one possible explanation would be differences in the relative swim bladder size in comparison to body size of bluegill and crappie. The relative swim bladder size could affect the available space for the swim bladder to expand within the body without causing physical harm or damage to other organs. So here are the papers that assisted us in the presentation and the background for our research. And before I go, I'd like to give a special thanks to the others who helped contribute to this research. I'd like to thank our guides up in Wisconsin, Logan Cutler, Bradley Gumtout, and Chris Jones. I'd like to thank our other anglers who assisted us in the capture of fish, Nathan Brand and Mitchell Brown. And then I'd also like to thank our other contributor, Dr. Corey Seski, who helped supply us with some of the supplies that we used in this study and also helped us obtain our eAEC protocol. Thank you for listening to my presentation today. Have a great rest of your day, and I hope you enjoyed this presentation. Thank you.